So we're continuing on with the Unit 1 packet, Section 3 or Lecture 3. This is a topic called Residuals. It's an interesting topic because it's specifically related to linear regression and whether or not a regression model is a good fit for a data set. So, you know, it kind of begs the question of when you're talking about a model, trying to model a situation, is a linear model the most appropriate fit? Because it could, contextually, it could be a good fit mathematically, but will it be a good fit contextually? Right? And any mathematical analysis we do isn't really going to get at the heart of that. That's where your own senses are going to come into play. But what this is another tool that'll help you determine mathematically whether or not a regression model, specifically a linear one, is appropriate for a data set. Right? So the first couple of pages, you could read through this, but I'm going to walk you through a couple of examples. This page, 16 and 17, you just read through it, and also the textbook in the indicated topics on Blackboard, just to get a more background if you'd like. The textbook isn't really necessary, I don't think. I didn't plan it to be necessary, but it's always there if you need it. All right, but we're going to jump right to the example on page 18. An employer gives an aptitude test to his employees and compares it with their productivity at work. The results are given. We're going to draw a scatter plot, come up with a correlation coefficient, all that good stuff. Determine whether or not there's any outliers or influential points, and then we'll go from there. We'll get into the residual component of it, and I'll show you why that's important and how it manifests itself. So let's get our Desmos calculator into the party here. All right, so again, to type the data in, table. Now, in this case, they gave us X is the score on the aptitude test and Y is the productivity level. Even if they didn't tell us that, I think it's common sense that aptitude would come before productivity. Like how good you will be at something before you actually do that something. It seems to make sense. So even if they didn't tell us that aptitude was X and productivity was Y, I think we could have surmised that ourselves. All right, so getting our data points in, popping them into the old calculator, not using any fancy scripts that we may have written together. Anything stored on Blackboard, we'll just do it using the built-in functions that Desmos has to offer. And if I can say another sentence or two, I will have bought myself enough time to type in the data. All right, so just a quick double check, make sure I didn't totally screw that up. That is always the plan, as they say. Draw a scatter plot of the data, label and scale the axes. Well, Desmos is going to label and scale it for us, so we're not worried about that. Well, at least it'll scale it for us, so we're not concerned with labels as much as maybe we would be if we were doing it by hand. Is there a pattern? Well, we'll get there. We've got to take a look at the picture first. All right, does the data appear to be positively correlated, negatively correlated, or neither? All right, well, all stuff that I can't answer. I can't answer it yet. I haven't seen the picture. So let's zoom out, pinch out. We look at the picture here. Looks like almost the Big Dipper, I guess. I don't like the viewing window here. I like it to be relatively consistent with the data that's provided. So I'm going to tap on that little wrench there. The x-axis, those are related to the x values. The smallest value there, it looks like 3. Largest is 20. So I'll go 0 to 20. Maybe I'll go 0 to 25. Go a little bit north, south of the lowest, north of the largest. And same thing for the y's. Well, I guess for the x's it would be east and west, or west and east, to be precise here. 0 and I guess maybe 100. 70 is the biggest, so And then we can pinch zoom from there. I mean, it's pretty not bad. You know, if you want to bring it in a little bit, that's fine. We get a nice little scale there. It's pretty obvious what the scale is. You know, just counting tick marks. I'm going to screen grab that, pop it right in. This is a quick copy job. Done. I guess I'll save it. I tend to save these things. Paste it right in. Oh, new feature that I was unaware of. It's honestly, it's probably not a new feature, but I stand by the fact that I was unaware of it. Okay. You know, it doesn't hurt to throw some labels on here. It's simple, X and Y. All right, so is there a pattern? Kinda. I mean, we've got these couple of points here. Seem to be a little out of whack. If we can get rid of those, I think we'll be in pretty good shape. All right. Unfortunately, you can't just disregard points without having a valid reason to, but we can at least kind of pretend like they're not there for the time being and just kind of write our conclusion here as if they're not there. All right, so what I would say is something along the lines of, if those two highlighted points weren't there, we would have a positive trend, a strong positive trend. I mean, it's not unreasonable to say that. All right, so that's where I'm going to go with it. I mean, it's just a question of, you know, what makes sense. All right, and so if you do include those values, I don't even know what you would say. You know, like, would you say it's increasing and then it shoots off to the left and then off to the right and then that's it? I doubt it. So I think it makes sense to be as specific as possible, of course, but you got to make some concessions along the way, and this is the one that I'd be looking to make. All right, so I would say here, if we disregard the highlighted points, it appears that there is I would say maybe a strong, kind of covered myself with the appears comment. It appears to me. So if somebody said, no, it doesn't appear that way. Well, to you, to me, it appears as if what exactly what I'm saying is true. All right? So you can kind of create a little wiggle room for yourself there. It's a good thing. It's something that you want to. They're qualifying words that you want to be able to, you know, take advantage of, just to cover yourself. All right? It appears that there is a strong, positive, linear. You could say relationship. You could say correlation. I'm going to say correlation. All right. Is there a pattern? Okay. Well, strong positive. Linear would be the pattern. Okay. Correlation. Oh, well. Turns out they asked for that anyway. So there we go. All right. Now we have to find the correlation coefficient. All right. Now, we made the claim that it appears to be linear. Without those points, it appears to be linear. I don't know what function would go through. I mean, on the previous page, we talked about quadratic, cubic, and all that stuff. I mean, are you going to say, okay, it's a rotated normal distribution? I doubt it. What we would say is, you know, you go with the more obvious thing. Right? And so the more obvious thing is that it would be some sort of, you know, linear relationship. All right, but once you make that claim, we're calling it linear. That's the correlation coefficient that we're looking for. All right. So if you said it appears that there's a quadratic correlation here, then you would not be wise to then find the linear correlation coefficient to analyze the strength of the relationship between the two variables. All right, it's just it would not play out well. It would not be correct. Right, so what we're going to do is tap in our y1 tilde a plus bx1. Gives us lots and lots of information. I kind of zoomed a little bit here somehow. I'm not really sure how I did that, but it happened. And it looks like we have an R value of approximately 0.444. All right, does it support your answer to part A? Well, kinda, I guess. That answer that we came up with, if we disregard the highlighted points, then there would be a strong positive correlation. So anytime we would include points that are off that track, off that trend, it would reduce the correlation coefficient, right? So we assumed a strong positive correlation if the highlighted values were removed, highlighted, I don't even know what I was writing there. Highlighted values were removed, including those values would only serve to reduce the value of R. I mean, it would strengthen the argument if you included the fact that they were off the trend line, but I mean, we're referring to highlighted values, highlighted points. All right, so it's pretty clear that your attention is directed to the diagram in which there are highlighted points. All right, so we're making use of the diagram as part of our write-up. All right, find the regression equation. All right, mission accomplished without even trying. So y hat for the proper or appropriate. Which one am I going for there? I'm not sure, so I'll say them both. Appropriate. Notation. So 25.845-ish plus 1.546 times the value of x. That's just to plot it on your plot. Right? Sketch it on your scatter plot. So there's a couple of ways we can handle that. One would be to just roughly eyeball it and put it on there. The other thing would be to do another screen grab and replace the one I had there or have there with the new one. You know, it's one of those pitfalls when you don't read all parts of a question before you get started on the solution, but it's not really a big deal. I mean, it did say sketch, so I will in fact do that. So about 1 3/4 above it, and then I'll use my line draw tool to plop it in there. All right, so this is Y hat, poor quality hat. That's not going to protect anyone from the rain. Discuss any outliers or influential points by visually looking at the graph or at the scatter plot. Well, what we're really saying here is that there are some points that are striking deviations from the overall trend of the data. Not necessarily the trend line, but the trend of the data. What are they? Well, the points that we disregarded, those seem to be the ones. Because if they weren't there, we'd be in pretty good shape. All right, so the highlighted values show a striking deviation from the overall trend of the data. making them outliers. All right, we're not earning any prizes for grammar here, as you know, because I am not the best influence when it comes to that. Now, influential points are a special case of outliers. Right? So one of them could be an influential point, but we're not really sure which one, or maybe both, would be considered influential points. So what we want to do is remove anything that we suspect to be an influential point and recalculate the regression equation and see if there's any kind of significant impact on the model itself. All right, so what I'll do is I'll just take a look at those highlighted values. This one up here is 870, and this one is the 2040. We don't remove them together, we remove them one at a time. All right, so what I would do here is I'm just going to kind of make a little note here. Remove 870, and then over here remove 2040. All right, those are my two suspected values. All right, those are the ones that are off the beaten path. And then all we're going to do is recompute the linear regression equation. So I just removed the 2040. All right, so why did I remove that one first? It's the first one I saw. All right, there's no rhyme or reason other than that. So y hat, when I remove that, is now 2.3-ish plus 5.0985. All right, now what I'll do is remove the 870, but in removing it, I'll just replace it with the 2040. All right, so the 2040 gives a y hat of about 22.293 plus 1.591x. All right, so did they in fact make a significant difference to your regression line? Well, you know what I could do, if we really want to look at it like carefully and analytically, I can plot them all right, all in one shot. I'll put in my y equals 22.293 plus 1.591x. All right, whoa. Oh, okay. I confused myself there for a second. I was like, that's exactly the same as regression line. Well, it should be, because that's where I got those numbers from. All right. I do have to add the 870 back in. Thought I discovered something new. Nah. What I thought I did was I thought I screwed something up, which is, of course, more typically the case. All right. So let me get all the points in. So the 2040 I have to chuck back in. Oh, correction, the 870. All right. So what we're going to do is we're just going to look at them. So here, this the 25.845. So this guy here, the one that's blinking, that's the correct linear regression model with all the data points included. All right. So if I turn off all of these values, this is where we started. All right. This one is what I get if I remove the 870. I'm not noticing much of a difference. All right. The y-intercept's a little different, but the overall trend of the data, essentially the same. Completely different equation. Massively different. Let me change the color so it even... Oh. I'll make it purple. So it makes it pop a little bit more. All right. So, like, wildly different. All right. So that's what the equation would be if only the 2040 was removed. All right. So that 2040 had a major impact on the the nature of the equation. Whereas, that initial value, not, that other value of 870, even though 70 is much bigger than 40, not so much. All right. The reason why is it all has to do with the slope. All right. So what I'm going to do here is just kind of take this back for a second. I'm going to reduce this in size and just talk to you about slope for a second, because that's where the context comes into play. All right. So slope in this context, because it's always change of y or change in x, right? It's a video. I'm expecting somebody to say, yeah, right, absolutely. Great observation. Change of y over change in x. But y represents productivity. And x represents the change in aptitude. Or x is the aptitude, I should say. All right. So the interpretation here is, and I'm going to bring this in so I can actually write it. For each unit of change in aptitude, there is, and I'm just going to put a blank here, blank units of change in productivity. All right, this is a very important observation, because this is the key to everything. Which, I don't know how I can make something sound any more important than that. All right. So this is the Luke Skywalker of the battle against the Empire. All right, that is this problem. All right, for each unit of change in aptitude, there is blank units of change in productivity. That's what the slope means. So take whatever your y value is, that is the numerator in your slope, and whatever your x value is going to be your denominator. But this is what the interpretation is. All right. So what that means in this case is, with all the data points included, for each unit of change in aptitude, there is 1.546 units of change in productivity. Now, productivity is like what? Jobs completed. All right. Well, what if you're building a car? All right. So one more point in aptitude produces 1.546 more cars over whatever predetermined period of time. That's great. All right. So your 1 unit of aptitude is worth roughly 1.5 units of productivity. All right. Now, if we remove the 870, all right, so what that is a person who had a low aptitude, all right, the 870, a low aptitude score, and we don't know what the max is. Like, was this out of 100? Was this out of 20? We don't know. But the person who had a score of 8 had a really high productivity. All right. So the test that they took said that they weren't really going to be that great at this job, or at least they weren't going to be too much more above average than some of the other values. Like let's say the max score is 20. So and 10, let's say, is average. It's hovering right around average, a little bit below. All right, so is the 9. A lot of values are below average, but maybe the max score is 50, and all these folks are not so good. All right, but that's what we're going with. Just some idea that that 8 is possibly a middle of the road score. All right, but that individual, even though they tested poorly, maybe they had a bad day, maybe they were sick, their productivity is off the charts in compared to everyone else, or in comparison to everyone else. Why? Because maybe they got sick the day of the aptitude test. Maybe they didn't take the aptitude test seriously. Maybe they don't take tests well, but they're really good workers. There's lots of different possibilities. All right. On the other hand, that aptitude score of 20 is an individual that didn't really appear anyway to live up to the expectations any more than a person who performed half as well. All right, so that 40, yeah, it's higher than most, but it's not high enough to explain the aptitude score of 20. All right, so a person that tests well but doesn't apply themselves. Some of us were those people, and some of us know those people. The student who's really bright, but they never try in school, so they don't get good grades. But but he's really smart, but they only get like 60s and 70s on tests. It's like, what's going on here? They're just not applying themselves. Possibly, that's a possible explanation. All right. One of them is kind of an error in one way, and the other is an error in the other way. Which one's more important? The one that affects productivity. All right. So if you look at the 1.591 at the bottom here, so let me emphasize that. If I look at this one compared to this one, removing the score of 870 brought the 1.546 up to a 1.591. Not much of an impact. All right. So we're still concluding that on average, that for each unit of change in aptitude, there's about 1.5 units of change, and maybe we can call it 1.6 units of change now in productivity. But if you remove the 2040, the bright but not so motivated individual, now the score, the slope value goes up to over 5. So for each unit of change in aptitude, there's a roughly 5 units of change in productivity. So let's say, again, productivity is measured in number of jobs completed. And what if those number of jobs is like you're building cars? Like just 1 unit of change in aptitude could lead to you're going from 1.5 cars being produced to over 5 cars being produced just by 1 point of change in aptitude. That's substantial. So then it begs the question, well, which one is correct? We don't know. So more data is required, but this is a conversation worth having, because then if you're running this company, aside from that 2040, you would want the individual who has a higher aptitude, because you're going to get more productivity out of them. All right. So to answer the question, did they in fact make a significant difference? Yes. The slope changed significantly. All right. So, there's kind of like a little gray area here in terms of answering a question. I want all those thoughts to go through your head, everything that we just talked about, or I talked about, but I'm not going to make you write all that down, because that would be an essay. Like the whole test would be this one question, So, but I want you to think about that sort of stuff, because that's really why we do this. All right, so we're going to move on to the next page, which is a continuation. It says, construct a residual plot and discuss its implications. All right, so that goes back to the reading on the last couple of pages prior to the one we just did. The good thing about a residual plot, now, a residual plot is related to the original data set. So if you want to just delete these values, you can. Although, we'll just hang on to this one, because eventually we're going to have to work with the influential point. So we'll just keep that just in case. All right. So here's my original data set. Now you see here this little icon that says, well, it says plot, but right above it, it says residuals. So you can kind of guess what that means. You tap on that, it turns a residual plot on. All right. Now it's like, oh, hey, man, this is so confusing. There's so much stuff going on. What do I do? Well, all I want is the residual plot. So I'm going to turn off my regression line. And then I'm going to go up here, and you see now we have a new column, that blue column there. That's the residual plot, and this is your original scatter plot. All I want is the residual plot right now, because that's what we're going to analyze. All right. Now, if you read through those previous pages, then you'll understand everything I'm about to say. If you didn't, then I'm going to tell you to pause the video and go back and look at those pages for a couple of seconds. It's not much reading, so that's the thing. Like, hopefully you paused it already and took a look, but I didn't explicitly tell you to do that, so that one would be my bad, I guess. But definitely, in this moment, if you're worried that you're not going to understand what I'm going to say, then pause the video and go back and read pages 16 and 17. All right, so if you're with me right now, I'm assuming that you're ready to carry on. Discussing the implications of a residual plot is very simple. All we have to do is look at it and say whether or not we see a discernible pattern within the data set. All right, if you see a discernible pattern, then a linear model is not an appropriate fit. If you don't see a discernible pattern, so the data points are scattered in some way that doesn't show a function pattern, all right? So one of those things that we talked about, and I'll just kind of flash right over here to page 15. On this page, the quadratic, the cubic, the quartic, the exponential, natural log, all right? Those kind of patterns. If you don't see one of those patterns, then we can assume that it's going to be an appropriate fit for a linear model. So no pattern, linear fit, is appropriate. Any pattern, any noticeable. Okay. Confession, not 100% sure how to spell noticeable. If it's Noticeable or if there's no E there. So I am pretty confident that I can spell the word clear. So that's the one I'm going to go with. Why I'm going all caps here, I have no answer for that. All right. Any clear pattern, linear fit is not appropriate. All right. Unfortunately, or fortunately, depending on how you look at things, it's in the eye of the beholder. I look at this and I say, well, I don't see a pattern. So this is what I'm going with. All right. You might look at it and say, well, if I blur my vision and I'm really careful, I can go like this, and then I can come back down and grab that. Oh, okay, well, that wasn't supposed to happen. But you get the idea. So something like this, I'm using my Robin Williams voice. And now we're looking, oh, cool. You know, okay, maybe some kind of cubic. I don't know. But maybe you can find a pattern. I just don't see one. So I'm thinking a linear fit is appropriate. That's all this question is asking you to do, one of these two things. All right, if you see a pattern, then a linear fit is not appropriate. Now, this is the thing that confuses people. If the pattern is that of a straight line, so if you see points, I'm like chuckling to myself here. If you see points that are organized in a straight line like this, that's a pattern. So even though it would be the pattern of a line, it would mean that a linear fit is not appropriate. Right? So it's a quirky aspect to residual plots, but it's something that you need to be able to recognize. Because whether or not, because we talked about this for the other types of regression models, whether or not a linear model is a good fit is really important, because like you don't even have to look at these other possibilities if you've concluded that a linear model is appropriate for a data set. All right, so that I can't emphasize that enough. All right, so what proportion of the variation in productivity can be explained by the aptitude test? Now, proportion of y, all right, because productivity is the measure of y in this case, not always, but that's a y variable. Oh, that's a little too thick now. Can be explained by the aptitude test. Aptitude test is a measure of x. All right, so if they ever ask you for the proportion of variation that can be explained, all right, so the framework of the question will always be something that's written in green. Not the question won't be written in green, but what I have here highlighted in green is what I meant to say. That is asking you for the r squared value. All right. So this is asking for r squared. All right. So if I say, what is the proportion of variation in the weight of a person that can be explained by the number of cookies they've eaten, from that question on page 15, I'm asking for the r squared value. Proportion of variation in y that can be explained by the aptitude test, asking for the r squared value. It's proportion of variation that can be explained by, right? Y, then x, right? That is the definition of the r squared, right? Contextually, or at least theoretically, which is the opposite of contextually. Including the influential point, so that means all points together. Well, we have that here. So that is approximately 0.1975, which we could say 198. We're using the approximate symbol, so we're covered. We can do our rounding, not including the influential point. Right. So in that case, I need to get rid of that that last value, because the 2040. I'm sorry, not the last value. The 2040 is the one that has to go, because that's the influential. All right. So everything but the 2040 is now included in here, and now my r squared value has jumped up to about 0.617. That is a massive jump. It went from like 0.2 to 0.6 in terms of the strength of the relationship between the two variables. All right. Now, what does a proportion of variation mean? I kind of oversimplify the definition in the sense that I kind of imagine it as you have your two variables. One of them is a father, and the other is the son. All right. Father and son are walking. They're walking off into the distance. I should use consistent colors. For whatever length of movement that the father makes, you're thinking in terms of footsteps. The father takes one giant stride, right? The father is much bigger than the son. The son is just like the father, genetics in common. So the father is taking with his little tiny legs. I'm sorry, the father is taking with his little tiny legs. The son is taking with his little tiny legs the same type of stride as the father, except it's going to be much shorter because his legs are much shorter. If I can get it going in the same direction, that would be ideal. All right. So they're going in the same direction, and they're going in the same direction in the same way. There's a relationship, father-son, right? So that's relationship in a different level. But here we have a 100% stride. Here it's a 60% stride, approximately. All right. So that's what the r squared is telling us. All right. So the r squared is telling us, as one variable moves, as there is movement in one variable, what is the percentage of movement in the other variable? All right. So if you have that father, son, mother, daughter, however you like it, come up with your own analogy. If you have that kind of relationship in mind, then it's pretty easy to come up with the proper solution. All right. Or at least the proper interpretation, I should say. A new job applicant scores a 9 on the aptitude test. The employer wants to predict, because he hasn't hired him yet, all right, or her. Oh, well, his productivity level, so him. Help the employer use a regression equation without the influential point. All right, so here's my regression equation without the influential point. I rewrote it in. All right, so we know that the x value is 9. We want to know what the y value would be that corresponds with that. What is the level of productivity that we can expect from this employee, potential employee, based off of this number? So what we would want to do, we can do it one of two ways. We can rewrite this y so it's an f of x, using that function notation. you could put a few more decimal points in if you want a little bit more accuracy, but then if you write f of 9, that figures out the y value that corresponds with the x value that we're given, the y value that corresponds with the x value of 9. So f of x is equal to 2.3 plus 5.0985 x. Without doing any number crunching by hand, we get about 48.187. All right. That's really, I mean, if you think about the number of things from, honestly, I don't know what the prerequisite for this class is anymore. It used to be college algebra or trig. I got to imagine it's something along those lines, but maybe it's just college algebra now without the trig. There's not much trig in this class, so there's not really a necessary, there's no need for people to have a mastery of trigonometry. But things like function notation you should know, but if you don't, you can always just kind of go with the flow here and say, okay, well, he's saying that just replacing the 9 is the same as saying, replacing the x with the 9 in f of x, making it f of 9 is the same as replacing the x in the function with a 9. Right, and that's what it is. It's a side-by-side replacement, right? If you don't like that, then what you can do is just write 2.9 plus 5. Oh, that's not a 5. 5.0985, and then manually plug in the 9. The problem with that is, I mean, let's think back to page 15. There's some pretty big equations there. If you have to do it with one of those, you might run into a problem. All right. We should have units. Now, in this case, I don't think they told us units. Productivity at work. Well, so we could say units. We could say jobs completed. Just come up with some unit that makes sense for the context of the problem. I'll leave it as units just to keep it, as general as possible. But depending on the question, the units might be a measure of distance. X could be the octane of gas or the amount of gallons of gas in the car. Any number of possibilities. With Y being the amount of miles traveled. On the particular tank. There's a lot of different possibilities, but you want to be thinking about the units. Right? Any question I give you on a test, it'll be clear what the units are, or I'll tell you to disregard units. But that's a different conversation for a different day. All right, so that is